So, welcome to lecture 37. So, in this lecture I am going to discuss about vector spaces versus free modules. So, basically we have already seen various properties they are holding for vector spaces, but they are not true for free modules over arbitrary rings. So, let me start the lecture. For vector spaces over fields, any two bases have the same cardinality, but this is not true in case of free modules over arbitrary rings. So, now I am going to give example for this one. So, for that one I will start with example E4. So, let me start. Let V be a vector space. So, over a field K, let V be a vector space over a field K of dimension. Every vector space has a dimension which is the cardinality of a basis. Dimension countably infinite. Okay. So, countably infinite dimensional vector space V I started. So, now let me take R, this is equal to end of V over K. So, this is just a notation. So, endomorphisms from V to endomorphisms on V which are K linear, it means that all K linear transformations from V to V, set of all F such that F from V to V, this is a linear transformation, okay, it is a linear transformation over K. So, and we know that R is a ring, it is a non-commutative ring, okay, it is a ring with addition of linear transformations, addition of maps, okay, that is our addition, and composition as multiplication, okay. So, therefore, R, this is a ring, and of course, R is a non-commutative ring. So, now let us come to take, so let take it as M is equal to R itself, okay. Then of course, M is a left free R module, with basis, as usual this I am using several times. So, with basis singleton 1 means just identity map. Here 1 is identity map, where 1 is a map from V to V such that 1 of x. So, this means x. So, for every x belongs to V, okay. So, identity map, okay. So, then M is always a left free R module, with basis singleton 1. So, now what we prove is, we prove that given any positive integer n, there exists a basis, okay, Bn of M over R there exists a basis Bn of M over R having n elements, okay. So, that means that I have, if you give me any n positive integer, we are able to produce a basis consisting of n elements. Thus, we have several bases of several cardinalities, okay. So, this we are going to show now. Okay. So, for that one, let me start. We started with a vector space of countably infinite dimension. So, let me start with the basis. So, let E1, E2, E1, E2 and so on. Okay. So, this is contained in V, this be a basis of V over the field K. Okay. So, countably infinite basis, I am call it as E1, E2, E3 and so on. So, for this basis, so okay, I am denoting as B. Now, let us define. So, F1, F2 and so on Fn, okay, these are all belongs to linear transformations from V to V, K linear transformations from V to V as follows. Okay, I am defining F1, F2, Fn, these are maps in the following way. So, F1, so F1 we define as, so F1 of Ej, so this is E k plus 1, okay, if j is equal to, so k n plus 1, okay, for some k, of course greater than or equal to 0, integer, non-negative integer and 0 otherwise. See, to define a linear transformation on V means it is enough to prescribe the values of F1 of the linear transformation on the basis only, okay, that is only we are doing. So, for any j, okay, for j, okay, greater than or equal to 1, okay. So, this is F1. Similarly, F2 of Ej, so this is defined as E k plus 1 if j equal to k n plus 2 for some k greater than or equal to 0 and 0 otherwise, okay, and so on. So, what will be our Fn? So, Fn of Ej, so then this is E k plus 1 if j is equal to, so k n plus n, so for some k greater than or equal to 1, greater than or equal to 0 and 0 otherwise, okay, okay, understand. So, that means if I am writing Fi of Ej, so it is defined as E k plus 1 if j is equal to k n plus I, okay. So, for some k greater than or equal to 0 and 0 otherwise, okay. So, each Fi, so we are defining in this way, 1 less than or equal to I less than or equal to n and for all j greater than or equal to 1, okay. So, once I prescribe Fi's on Ej's, then we know what is Fi is, a linear transformation. So, now let Bn as this F1, F2 and so on comma Fn. Now, our claim is this Bn is a basis of, this Bn is a basis of M over R. Our M is of course R only, okay. This is a basis of R over R. So, first we will show that means that I need to show that Bn is linearly independent and it is spanning or it is a generating set of M over R. Now, let us look at the proof. the first one is Bn is linearly independent. Okay. So, the first one we are going to show is Bn is linearly independent. So, for that one, let me start with some, that means I need to show, suppose summation alpha I composition Fi I from 1 to n, suppose this combination equal to 0 for some alpha i's belongs to R. Okay. Okay, here what is our R? Just this is the linear transformation, k linear transformations defined on the vector space V. So, suppose this is summation alpha I composition Fi equal to 0. So, that means this map is 0 means evaluated at all the basic variables also, it is all the basis elements also it is 0, that means summation I from 1 to n alpha I composition Fi. So, this evaluated E kn plus certain j. Okay. So, this is equal to 0. So, for any k greater than or equal to 0 and for all j greater than or equal to 1, okay, for all j greater than or equal to 1, this is true. Even I can take j lies between 0 and 1 also. Okay. So, 1 less than or equal to j less than or equal to n. So, but according to our definition of Fi, so what is our definition of Fi? If you just see, then definition of Fi is Fi of Ej is Ek plus 1 if j equal to kn plus I. So, therefore, by definition of Fi, so then this is only one term is surviving. So, that is, so I equal to j term. So, that is summation. So, that means what I want to say is, so then this is alpha j of Fi of E kn plus j, this is the only term is surviving, rest of all terms they are zeros. So, but what is this? This means alpha j of Fi of kn plus j, this is E k plus 1. So, then this is equal to 0, and of course, this is true for every k greater than or equal to 0 and 1 less than or equal to j less than or equal to n. Okay. So, that means alpha j value is 0 and alpha j of this En, this is equal to 0 for all n greater than or equal to 1. So, that means that our map alpha j is identically 0, okay, for any j as required. Okay. So, therefore, Bn is linearly independent. Therefore, Bn is linearly independent. Now, we will show that Bn spans, Bn generates, this Bn generates M over R. Okay. So, that means that if I take any f belongs to M, okay, M is same as R. So, but this is same as endomorphism V, of course, k linear maps from V to V. So, for any f, what we need to show? For any f to show there exist, so there exist, okay, so there exists some alpha 1, alpha 2 and so on comma alpha n, so which belongs to R, such that our f we can able to written as summation alpha I composition Fi I from 1 to n. Okay, that is the meaning of F1, F2, Fn generates M over R. Now, let us start with one arbitrary f belongs to M, f belongs to M. So, now now let us define alpha 1 alpha 2 for this f. Now we will explicitly describe what is alpha 1 alpha 2 alpha n, so that our f is equal to this sum of alpha I composition fi I from 1 to n. So define alpha I as in the following way. Define alpha I, of course 1 less than or equal to I less than or equal to n as the following way. So alpha I of E k n plus 1, so this is equal to f of E k n square plus I. Okay. Alpha I of E k n plus 1 is equal to f of E k n square plus I, and alpha I of E k n plus 2, this as equal to f of E k n square plus n plus I, and so on. Alpha I of E k plus 1 n, so then this is equal to f of E k n square plus n minus 1 times n plus I. Okay. So for any k greater than or equal to 0, okay, so one can define, and 1 less than or equal to I less than or equal to n. So it was defined like this. Okay. Alpha I is defined like this, prescribed on these basis values. So then now the claim is our f, this is equal to summation alpha I composition fi I from 1 to n. Now let us see the proof of this claim. Now let me start with the right hand side. So consider summation alpha I composition fi. So this I from 1 to n, so evaluated at E k n plus j, okay, k n plus j for any k greater than or equal to 0, of course 1 less than or equal to j less than or equal to n. So this is equal to summation I from 1 to n alpha I of fi evaluated at E k n plus j, okay, summation I from 1 to n alpha I of fi E k n plus j. So but according to our definition of fi, so what is this? So then this is alpha j of E k plus 1, okay, this by definition of fi. Okay, rest of all terms will be 0, surviving with only this term. But this is, let us written as alpha j of E. So k, let us written as some k dash n plus L for some L 1 less than or equal to L less than n. I am dividing k by n. So k dash is quotient and L is the remainder. So then this is k dash n plus L plus 1 as it is I am writing. Okay. So this one. So now what is alpha j definition? Let us use the alpha j definition. So then this is precisely f of E k dash n square plus L n plus j. Okay. So by definition of alpha j as defined above, by definition of alpha j, so f of k dash n square L n plus j, this is the one we are getting. So now this is equal to f of E k dash n plus L times n plus j. Okay. But what is this? This is precisely equal to f of E k n plus j. Okay, f of k n plus j, and this is true for every k greater than or equal to 0 and 1 less than or equal to j less than or equal to n. So, thus what we initially started with this expression. So, therefore we have summation alpha I composition E I alpha I composition F I from 1 to n this E k n plus j, this is equal to f E k n plus j, k n plus j for every k greater than or equal to 0 and for any j lies between 1 and n. Okay. So, that means that summation I from 1 to n alpha I composition f I. So, this is equal to alpha I composition f I, this is equal to f. Okay. So, therefore, f is linear combination of f1 f2 fn. So, therefore, this Bn is a basis. So, it is a basis of M over R. Okay. So, free module we find one basis Bn, but what is the cardinality of Bn? Cardinality of Bn is n, and cardinality of Bn is equal to n. Thus, if we give any integer n, we can able to produce a basis of M over R containing n elements. So, that means that we can find so many bases of so many cardinalities. This finishes the proof of this example. So, thus for various values of n we will get various bases, but we will prove that this is not true in case of free modules over commutative rings. I will give the proof of that.